Imagine you are a doctor in a busy hospital. A patient walks in, but you cannot run every test. Some tests are quick and cheap, others are expensive but give a lot of information. With a strict budget and limited time, which test do you choose? Or picture yourself as the editor of a digital magazine. You only have 2 ad slots per issue, but 10 advertisers are knocking on your door. Each offers money, each needs space. But once the page is full, that's it. Which advertisers do you select? Different worlds, medicine and media, but both hide the same computer science puzzle, the zero-one knapsack problem. We have already learned that the zero-one knapsack problem is hard to solve because its decision version is NP-complete. That means if we rely on brute force, large cases become practically impossible. It could take years to compute. Dynamic programming comes to the rescue. It gives us a way to solve the problem more efficiently. But in reality, it's pseudo polynomial, not truly polynomial. Along the way, we learn the greedy approach too, where it works and where it fails. So, why keep studying this hard problem? Because it's not just theory, it's a way of thinking about trade offs, optimization, and decision making. And beyond theory, it appears in real life again and again. Before we dive into real life applications of the zero one knapsack problem, it's useful to look at some of its important variants. In the basic zero one version, we have a single knapsack and multiple items to choose from. But when we change how the knapsack or the items are treated, we get different versions of the problem. For example, if each item is available in limited quantity, say more than one but not infinite, we call this the bounded knapsack problem. On the other hand, if each item is available in unlimited supply, we call it the unbounded knapsack problem. Now imagine instead of just one knapsack, we have several knapsacks, each with its own capacity. In that case, the challenge is to distribute items in such a way that the overall profit across all knapsacks is maximized. This is known as multiple knapsack problem. Another interesting twist happens when items are described by more than one property. In the standard case, items have weight and value. But what if each item also had a volume and we had to respect both weight and volume limits at the same time? That becomes the multi-dimensional knapsack problem, also called the multi-constrained knapsack problem. And these are just a few. There are many other variants too, and each one opens the door to modeling a new kind of real world challenge. With this foundation in place, we are now ready to explore how the zero one knapsack problem appears in real applications. Imagine you are the editor of a popular digital magazine that comes out once a month. Each issue has exactly 10 inches by 10 inches of space reserved for advertisements. Since the magazine is in high demand, many advertisers line up eager to showcase their products or services to your readers. But there's a strict rule each ad can appear only once per issue, and once the ad space is filled, that's it. Now, every advertiser tells you two things how much area their ad will take and how much money they are willing to pay you. As the editor, you must decide which ads should you include to make the maximum revenue without exceeding the available space. This is exactly a zero one knapsack problem. Here, ad space is the knapsack capacity, each ad is an item. Space it takes is the weight, and the payment is the value. You either take an ad or leave it. Now let's jump to another world, the world of blockchain. A blockchain is a network of computers that collectively store and validate transactions. Each node has a pool of transactions waiting to be added to the chain. Every transaction has two properties its size, which depends on the information it carries, and the fee that the sender is willing to pay. A miner or validator is responsible for collecting transactions from this pool and packaging them into a block. But here's the catch a block has a fixed size. So the miner cannot simply include everything. Since the miner earns the transaction fee for the transactions they include, their goal is clear: maximize earnings while respecting the block size. If you think about it, this is again a zero one knapsack problem. Here, block is the knapsack capacity, each transaction is an item, the size it takes is the weight, and the fee is the value. You either keep a transaction or leave it. Now let's move into healthcare. Imagine you're a doctor in a busy hospital. A patient comes in and you want to run diagnostic tests, but you face three challenges. Each test costs money. The hospital has a budget limit, and not all tests provide equal information. For instance, a blood pressure check is cheap and moderately informative. A cholesterol test is costlier but gives better insight. An MRI scan is extremely expensive but provides huge diagnostic value. And something like recording age is free, but the information it gives is limited. Your task is to decide which combination of tests give you the best possible diagnosis within your budget. Once again, this is a zero one knapsack problem. Here, the hospital budget is the knapsack capacity. Each medical test is an item. The cost or time is the weight, and the usefulness of the test is the value. Finally, let us see how this connects to machine learning. In machine learning, features are like medical tests. Each feature adds some predictive power to your model. That is the value. But each feature also costs something: more data, more computation, or more memory. That's the weight. Just like in medicine, you cannot include every possible feature because of limits on resources. So, deciding which feature to include is essentially a feature selection problem, another disguise of the zero one knapsack problem. Here, the model's resources are the knapsack, features are the items, their cost is weight, and their predictive power is the value. So, we have seen four very different scenarios: allocating banner slots or event sponsorships, miners picking transactions for a block, doctors choosing diagnostic tests, and machine learning models selecting features. At first, they sound unrelated, but if you look closely, they are all powered by the same underlying idea: the zero one knapsack problem. This is a problem that's been studied for more than 50 years in computer science, and yet it continues to appear in healthcare, digital advertising, artificial intelligence, business, logistics, and so many other areas today. The zero one knapsack problem is not just a classroom puzzle, it's a lens through which we understand real world trade offs. Even though it is NP hard, we study it because it teaches us the limits of computation. It guides us on when to use greedy methods, when to rely on dynamic programming, and when to turn to approximations. So, the next time you see a doctor deciding on tests, an AI model deciding on features, or a magazine deciding on ads, remember there's a zero one knapsack problem behind the scenes. And that is why, even decades later, the zero one knapsack problem remains one of the most relevant and fascinating problems in computer science. Thanks for watching. Don't forget to like, share, and subscribe so you never miss what's coming next.